So our atomic physics unit focuses on the model of the atom and how we changed from the billiard ball model, a very simple model that just expressed atoms as the simplest indivisible units that there were. And in atomic physics, we look at how that model changed and how we ended up today with the quantum mechanical model here at the bottom. Now, along that way, there were a lot of very important steps and very important discoveries that were made. The very first one is what we're going to focus on. We're going to focus on the change in the experiments that led to the shift from Dalton's model, this simple indivisible sphere, to Thomson's model, which is that atoms are these things that are made up of discrete positive and negative charges. They're actually separate things that exist in the atom. Now, scientists already understood that we could charge objects and that these charges could move around. Benjamin Franklin did a lot of work on this. And actually, he was wrong at one point, where we know that it's electrons that move around if we charge an object through conduction, or if we charge an object through induction, just bringing an object near. We know today that it's the electrons that are actually moving around on those objects. What Benjamin Franklin got wrong is that he thought it was actually this positive fluid that was exchanged between particles, and that's what he called it. And that was what scientists believed at the time, that it was the positive fluid that was exchanged between different objects. Now, our understanding of the atom at the time could date all the way back to Democritus, another guy on a hundo. So Democritus here, his idea was that we could break matter down, but we got to a certain point where we couldn't break it down anymore. And his word for these small particles were atomos, or atoms, which was picked up by a teacher, John Dalton, in the 1800s. He came up with this theory of indivisible spheres based off of the chemistry that he did and the observations that he made when he was breaking molecules down. He found that in a molecule of water, H2O, he would always break down and he would have twice as much hydrogen as he had oxygen. And so he came up with this idea that all elements are actually made up of tiny particles called atoms. That was building off of Democritus' ideas. He thought that atoms of given elements are alike. Atoms of different elements are different. Chemical changes take place when atoms link up or separate from one another, and atoms aren't created or destroyed by chemical change. So that was kind of the current understanding of the atomic model. We were left with this billiard ball model, where atoms are the simplest bits of matter. We can't go any smaller than it, and they're just these spheres. Now, that doesn't really incorporate the idea of charges, and scientists at the time knew that they could charge objects. And it wasn't until our development of cathode rays that we were actually able to learn a little bit more about the atom and actually understand that it contained electrons. This is William Crookes. He came up with something called a Crookes tube, which is a tube with a partial vacuum inside. So inside's a partial vacuum, so that there was no air particles in the way that would ionize and kind of scatter the light. So it's a partial vacuum. Now, what they would do is they would run a high voltage through it. So we have a negative electrode here and a positive electrode here. And when they put a high voltage through it, they ended up with this green ray being produced. So you can kind of see here, there's this greenish ray. It's produced on this one end, and then it ends up over here. Now, the reason why we know that this is the end where it's ending up at is because it's kind of a little of an ingenious idea to put a mask or a barrier in the middle there. So in this Crookes tube, what they actually observed was that a ray was produced. They observed a shadow at one end. And based off of that, Crookes was able to make an actual inference. Crookes was able to say that, well, this is being produced at the negative terminal, at the negative side, because of where that shadow is. So these were negative rays. Negatively charged rays is what Crookes was able to understand about these cathode rays. Now, J.J. Thomson took these cathode rays and went a little bit further. J.J. Thomson is an important name, and this is a model that we kind of start with in this atomic physics unit, where he took these cathode rays and he actually observed how these cathode rays interacted with magnetic and electric fields. So the first thing that he tried to do is he tried to actually separate the negative charge from that ray, and he tried to do that using a magnetic field. He knew that charged particles interacted, or charged objects interacted with magnetic fields. So by bringing this magnet close, he could actually see that ray being deflected, but he wasn't able to actually separate out those negative particles. What he saw, because that ray was actually being influenced by the magnet, was that the ray itself was negative. And in order to confirm that, instead of putting a magnetic field outside of that charged ray, what J.J. Thomson did too is he also exposed that ray to negative and positive plates. So I have parallel plates here. This ray is produced at this end. When it hits these plates, it's deflected towards the top of this screen over here, and he had a detecting screen over there. Because that ray is deflected from the negative charge, we have our electric field. Now our electric field again is the direction a positive test charge would move. It would be this direction, away from the positive towards the negative. Now this charged particle deflects in this direction, which confirmed the idea that this was a negatively charged particle. So J.J. Thomson observed that a cathode ray could be deflected. So it could be deflected by magnetic and electric fields. The inference that he made were that these cathode rays were made up of charged particles. So this was the first evidence that we had that actually the atom could be broken down into smaller bits. It wasn't a neutral particle that was moving across. It was a charged particle. So we were able to take the atom and break off these negative bits, which we know now are electrons. And these negative bits were what actually composed that cathode ray. So that led to Thomson's plum pudding model. Now at first Thomson wanted to say that atoms were entirely made up of electrons. But then he realized, well, that can't be true because we do have neutral atoms. There are some positive substances that cancel out electrons' negative charges. But he did know that those electrons could be broken off. So there must be electrons present in the atom. Now, because this atom could also be neutral, there must also be a positive charge here. And the way Thomson believed it may have been orientated was that we had this positive framework where the electrons were just plunked in there, which is what plum pudding looks like. A chocolate chip cookie is another way to visualize Thomson's model. Now, eventually, Thomson had some very bright students who would change this model of the atom. Ernest Rutherford and Niels Bohr would come along, and they would actually discover other things about the nature of matter that would cause this model to fall apart. And that's what we're going to be looking at in future videos.